So the last colligative property we're going to talk about is osmotic pressure, but first I want to introduce what osmosis is. And so it's kind of the book definition. You can always tell when I rip a definition from the book versus when I put in my own words, because that is clearly not my own words. But essentially it's just moving from areas of from low concentration to high concentration. It's movement of solvent only. So if you don't have what's called a semi-permeable membrane, solutes are going to move around, they're going to even out. That's called diffusion. But if you have one of these semi-permeable membranes in place, then the solute can't pass through, only the solvent. So water can move around. And the same idea is going to happen. So diffusion means that our concentration is going to equal out throughout the whole solution. That's what's happening. Osmotic pressure, osmosis, is going to try to do the same thing, but it can only do it by moving water around. And so what happens is it tries to dilute the concentrated side to match the other side. And in the case of zero concentration on one side, it doesn't happen. But that's what's going on. And so that semi-permeable membrane just means, again, only the solvent can pass through it. So if I have a saltwater solution on the left, say it's 1 molar, I have a water solution on the right, what's going to happen is I have a semi-permeable membrane in the middle. So water can move back and forth, but NaCl stays locked on the left. So this side is concentrated, this side is not. So water is going to move. I'm going to get what's called a net solvent flow from the right-hand side to the left-hand side. And as that happens, this water level is going to drop, and this one's going to move up. And eventually, I'm going to get to the point where there's no net solvent flow. And here's what's happening. I get a height difference. The concentrations still aren't equal. But gravity starts pushing the column back down. And so what happens is there's a force pushing water to the left, and gravity is pushing it back to the right. And those forces equal out, and the columns stop changing height. They lock in at a difference. And so gravity is pushing this way, and so what do we call the force pushing back the other way? That is osmotic pressure. And so this height difference would be how we would measure osmotic pressure. And again, you still have to have the semi-permeable membrane. So this is the same setup just after some time. And so solvent has just kind of whoop, gone like so. All right. Now the equation is pi equals IMRT. So it's like pi equals, it's pi mart, right? It's like, you know, we got bi-mart, there's pi mart. All right. And so I have no idea why they settled on pi, big capital pi for osmotic pressure. I guess because pi is like the Greek p, but I don't know for sure. I is the Van Hoff factor from before, and now we're using big capital M. So molarity is back. So be aware, this one depends on concentration and molarity. R, I always tell you, you never know where the gas law is going to creep in. Well, there it is again, and this time we're going to use the liters, atmospheres per mole Kelvin flavor because we need a pressure. And so this would solve to get us atmospheres. Temperature needs to be in Kelvin, that's going to cancel. Molarity is going to cancel moles. Per liter is going to cancel liter, and all we're left with is atmospheres because I is unitless. And again, I'll leave the practice for solving the equation to the practice worksheet, so it might be a little bit longer one for this section. Maybe it'll be like 2 pages this time because there's some stuff I want you to solve. And so the last thing we're going to talk about in this chapter will be how to use something like osmotic pressure or freezing point depression or boiling point elevation to figure out what the molar mass of our solute is. And that's going to be what you do experimentally. So it'll help you out with the lab, and it's just an important calculation to know in general.